Okay, so this is 10-3, and now we're going to be switching to geometric sequences in series. Now, geometric sequence is different than an arithmetic sequence. With geometric sequences, from one term to the next, we're multiplying instead of adding. And so instead of having a common difference, now we have a common ratio. So if I have these geometric sequences we see here, from 4 to 8, I multiplied by 2. From 8 to 16, I multiplied by 2. From 16 to 32, I multiplied by 2. My common ratio is going to be 2. Now, we can also decrease our numbers, and that would be multiplying by a fraction here, as we see in our second example. But notice that it does not follow an arithmetic sequence pattern. We're not adding the same amount each time. Here we added 4, here we added 8, here we added 16, and so on. Now, the formula for finding the general term of a geometric sequence is different. This is the term or the formula that we have here. Still has the a sub 1 and it still has an n sub 1, but instead of having a d in the formula, we now have an r for the common ratio. So let's do our first example here. And it says find the 8th term of the sequence whose first term is -4 and whose common ratio is -2. So let's first write a general equation, a sub n, and we have our first term, which is -4, and our common ratio is -2, and then n minus 1. So that would be our formula. Now we want to find the 8th term, so that would be -4, -2 to the 8 minus 1 power. 8 minus 1 is 7. -2 to the 7th power times -4 is going to give us 512. And so that would be the 8th term in the sequence. Now we can also find the sum, just like we did with arithmetic sequences. So this would be the sum of a geometric sequence. Not quite a similar formula as to arithmetic sequences, but we have a 1 minus r here and 1 minus r to the nth power, however many terms we're adding up, and then we have our first term. So let's go ahead and do an example. It says find the sum of the first 18 terms of the geometric sequence. So we have s sub 18, and our first term, let's see, I guess I need to give you a sequence. Our sequence is going to be 2, -8, 32, -128, and so on. So our first term is 2, and then we have 1 minus, and our common ratio. So to get my r value, it's going to be the second term over the first term. So -8 over 2 is giving us -4 to the 18th power. And then in the denominator, we have 1 minus -4. So simplifying that, and you're going to need your calculator for this one, -4 to the 18th power is obviously going to give us something really, really big. You probably won't guess how big, but it's actually going to be -27 trillion, or I'm sorry, billion, 790,694. Very, very large number. And you'll notice that geometric sequences grow much faster than arithmetic sequences. Now the next one shows us summation notation again. And we're starting at 1, going to 10, and this is our formula right here. So we need to find our first term and our common ratio. So plugging in 1 here, 2 to the first power is 2, times 6 is 12. And our common ratio is actually this right here. Whatever the base is of your exponent is our common ratio. And from 1 to 10, we're summing 10 terms. So s sub 10 is equal to, our first term is 12, 1 minus our common ratio to the 10th power over 1 minus 2. And when we calculate that very large number, we're going to get 12,276. Okay. Now, the thing that's very different and actually really cool about geometric sequences is that we can actually find the sum of an infinite sequence. So we need to kind of think about what that actually means. We're saying that we can add up infinitely many terms. So this is the formula that we use, and you'll notice that there's no n in this formula. Well, that's because there's infinitely many terms. We can't put a number in for infinitely many. If our r value, the absolute value of it, is less than 1, then there is a sum, and we say that it converges. But if our r value, or the absolute value of it, is greater than or equal to 1, then it diverges, or it does not have a sum. So let's go ahead and flip to the next page and do a couple examples. Here it says, find the sum of the infinite geometric series, and let me give you a series here. If we have 3 over 8 minus 3 over 16 plus 3 over 32 minus 3 over 64 plus, and the series will go on because it's infinite. It does not end. So, just to remind us, our formula is S equals A sub 1 over 1 minus R. So this is my A sub 1, and my R value I need to figure out. So negative 3 over 16 over 3 over 8 is going to give me my R value. I can simplify this, negative 3 over 16 times 8 over 3. And we're left with negative 1/2. Okay, so the absolute value of negative 1/2 is in fact less than 1, which means there is a sum. Well, now we need to find out what that sum is. S is equal to A1, which is 3 over 8, over 1 minus negative 2, or negative 1/2. And 1 minus negative 1/2 is 3/2. 3 over 8 times 2 over 3 equals 1/4. So what this is saying is that if I was able to add up infinitely many numbers in this sequence, my sum would equal 1/4. Now on to our last example for this section. It says express 0.9 with that bar over it as a fraction in lowest terms. Well, let's think about that. 0.9 with a bar over it. That means 0.9999 and repeating forever. We could rewrite that as 0.9 plus 0.09 plus 0.009 plus 0.0009, and we could continue that. If you add all those up, it equals this, which is equal to this. Well, this looks like a series, and we can actually rewrite these as a fraction if we want. This is 9 over 10. This is 9 over 100. This is 9 over 1,000. This is 9 over 10,000. And so on. Well, again, this looks like an infinite sequence or series. So let's find our R value. And some of you might already see that it's going to be 1 over 10. But if you don't see that, we can go through the process of solving for it. So our R value is 1 over 10. And our first term is 9 over 10. So 0.9 is equal to 9 over 10 over 1 minus 1 over 10. That gives us 9 over 10 over 9 over 10. And we know that anything over itself is equal to 1. So what we've just shown here is that this is equal to 1. and that's if we can actually sum up all of those digits of that decimal off to infinity, we would get that being equal to 1. And that is the end of section 3 in chapter 10.